Chapter 10, Multiple Regression. 10.1, Multiple Predictors, Video 1. As I've been alluding to in previous videos for chapters 9 and prior to that, the review in chapter 2, we are eventually going to extend our regression to account for more than one predictor or more than one explanatory variable. That time is now. So let's see how we transition from simple to multiple by looking at what's called the multiple regression model. If you'll recall, when we were doing sample regressions before, they were actually called simple sample regressions. Simple meaning one explanatory variable, one predictor. And our regression equation was of the form y hat equals b0 plus b1 x, where the b0 was the intercept and the b1 was the slope of the regression line. And when we attempted to describe the population regression, the simple population regression, again, simple meaning one explanatory variable, then we had capital Y equals beta 0 plus beta 1 times x plus an error term, where the error term compensated for things that the equation did not, and specifically compensated for variability in the y that was not explained by the explanatory variable x. There were also some conditions on the errors. They had to be normally distributed and centered at 0, but let's not sweat that too much. So how do we jump from simple to multiple? Well, first, let's replace the word simple with multiple. And the words multiple here refer to multiple predictors or multiple explanatory variables or multiple x's. So how do we compensate for multiple x's? Well, we just tack on more x's. But the difference is we need these x's to be labeled differently but still look like x's, so we're just going to subscript them. So now our simple model, our sample model I should say, will still start with a y hat equals some intercept b0 plus b1 times an x, but now the x is also going to be subscripted with the 1 because we're going to add another term. There might be a second predictor, we'll call it x2, and it might have its own slope, b2, plus, and we can have as many as we want. So how far can we take it? Let's take it out to k. So bk, xk. So this would be an example of a multiple sample regression that has k explanatory variables or k predictors, x1, x2, all the way to xk. And we can make the exact same changes down here. Instead of closing shop after after x, we can subscript it with the 1 to imply that there are more x's, plus another x, x2, with its coefficient or its slope, beta 2, plus, and we can run that as far as we want. We'll cap it at k as well. In your actual homework, there will be a finite number of explanatory variables. There'll be 3, there will be 5, it won't be k. But generically, this would end at beta k times xk, plus we still have the error term to compensate for variability in the explanatory variable that's not explained by any of these, the variability in the response variable that's not explained by any of these explanatory variables. So what are we going to do with multiple regressions? Well, pretty much the same thing we did with simple regressions. We're going to test whether or not slopes are equal to 0, which is the same as testing whether or not an individual predictor is effective. We're going to do an ANOVA, which is testing whether or not the entire model is effective. We're going to calculate a coefficient of determination, which will answer the question what percent of the variability in the response variable can be explained by these collections of explanatory variables. And I believe that's all we're going to do in this section. Let me just scan real quick. Yep. So basically, it's just stuff that we've seen before, bumped up to the kth degree, if you will.